Hello, hope you're all well. I'm going to do a wee quick video as if it was a lesson in class doing practical electrical circuits. This is key area 4, and one of the first things you've got to do is get familiar with some common component symbols. Now, you don't need to memorise every single one straight away, but just get more and more familiar as time goes on, but definitely be aware of the very, very simple ones like cell, battery, resistors, lamps, right? You're going to meet those all the time. Eventually we're going to meet all of these. Of course, ammeters, voltmeters are also going to be met very, very early on, so make sure you know what these are. Now, in a cell or a battery, the long line is the positive side and the short line is the negative side. So both of these have the negative side to the right and the positive side to the left. Notice the difference between a cell and a capacitor. Capacitors with two equal sides. That's different to the cell. So make sure when you draw a cell it has a distinctly different length of line here, so that you can tell the difference between a cell and a capacitor. Okay, so let's move on to the actual lesson then, but you will have to work on these yourself, memorising them, okay? So circuit diagrams, what are they all about? Well, a circuit diagram is used to make it easier to construct circuits or for others to understand what's going on. So when you want to pass on your information, you could explain it in words, which can take quite a bit of time. Often a simple diagram makes it much easier. And of course, a diagram is probably quicker once you know what you're doing. So there's a whole set of internationally agreed symbols for all the different components that make up the circuit. Everybody in the world should be using the same symbols, although there are some older symbols which are now no longer being used. So all the ones that you meet will be the same ones. Okay. So here's a circuit, right? So we'll call it circuit 1. And let's talk through the circuit and make sure you understand it. So when I look at circuits, I always start at the power supply. Now, at the circuit here, the power supply is at the top, and you can see it's a cell, and the negative side is on the right hand side, and positive side is the left. Now, so as we go around the circuit clockwise, we've got a switch here, and then we've got down here we've got a lamp or a bulb. There's a voltmeter, a resistor, and finally we've got an ammeter. So let's talk about how it works. So when this switch is closed, so when this comes down and makes contact with this, you're completing the circuit. So then the current can flow. It flows from the cell in a clockwise direction, because electrons always flow from negative to positive, because the negative charges are attracted to the positive side of the battery. Now, be aware, excuse me, some textbooks and websites use something called conventional current, which goes from positive to negative. This is not going to be used here, although you will see it elsewhere. Don't get confused with it, just ignore that. Current always flows from negative to positive. Okay? Now, all the different components there you have to recognise right away. The sooner you can get better at doing that, it will really help you in the rest of the course. Okay? So electrical current itself, let's talk about that. So electrons move around the circuit. They actually move. The rate of this flow is the current. A large current means there are more electrons flowing per second. So lots and lots of electrons, big current. Current is measured using a device called an ammeter, and it's got the units of amperes or amps. Often we'll use amps, but that's actually technically wrong. You should use ampere or simply the capital A. Informally, when you're talking, we often say amps, but we should probably try and avoid that. So an ammeter must be placed in series to take measurements. Now, in your house, typical currents will be all the way from 0 right up to maybe 13 amperes. Unlikely there'll be anything more than that. You can't get less than 0, of course. It can be thousandths of an amp. So these are okay. So here's a simple circuit. It's a series circuit. It's just got a few components, so let's kind of talk about what happens here. So we've got an ammeter. Now that ammeter measures the current flowing through the ammeter. So obviously anything that flows through here gets measured by this device. But it also measures the current that's flowing through this wire, of course, which is the same as the current through this wire, which is the same as the current going through this wire, which is the same as the current going through the bulb, and indeed the same as the current going through the resistor, and even it's the same as the current going through the power supply itself. So the ammeter measures the current flowing through the bulb as well as the resistor and also the cell. The current is equal at all points in a series circuit. In other words, the current from the supply is equal to the current at the first point, the second point, third point, fourth, whatever. However many points you measure it, it will always be the same in a series circuit. The current does not change. Voltage is a completely different thing. It's a measure of the energy carried by the electrons as they flow around the circuit. So as the electrons move around, they have energy and they will use up energy. Now the energy is used up by the components, like the cell, or not the cell, sorry, for example, a bulb or a resistor. In a series circuit, the voltage from the supply is shared with all of the components. So we could simply call it an equation that looks about like this, where Vs is the supply voltage and is equal to the first voltage, the voltage across the first component, whatever that component might be, plus the voltage across the second component, and the third, and the fourth, and so on, however many components there are in series. So it's always shared. So if you start off with, let's say, for the sake of argument, 5 volts, then that could be 1 volt, that could be 2 volts, that could be 3 volts, 4 volts, and 5, or it has to add up to 5. If there's only 3 components, it could be 1 volt there, 1 volt there, and maybe 3 volts here. Or it could be something else completely. The actual voltage on each component is harder to determine, but they must always add up to whatever the supply voltage is in the first place. I hope that makes sense. So let's look at working it all out. So in this circuit, we've got there's a cell here, which is a 1.5 cell, 1.5 volt cell. If the bulb uses 1 volt, what will the voltage by the resistor be? So if we've got 1 volt being used here, and we can think about that as similar to energy. So the battery is supplying the energy, so it's supplying 1.5 volts. This is using 1 of it, then that must be using the other wee bit that's left, the 0.5. Now you can do that simply by common sense, but you can do it by calculation. So here's how you write it all out. So Vs, the supply voltage, is equal to the voltage across the first component plus the voltage across the second component, whatever they are. So the supply voltage we've told you is 1.5. The first voltage that we know about is the bulb's voltage, which is 1.0. The second voltage across the resistor we do not know, and we need to work it out. So 1.5 equals 1.0 plus V2. So V2 must equal 0.5 volts. It's quite straightforward with a series circuit. So the V1 plus V2 have to equal the supply voltage, in this case 1.5 volts. So measuring voltage. A voltmeter is used to measure voltage. Typical values for batteries are 1.5 volts, 3 volts, 6, 9 and even 12 volts. Voltage from a main socket is 230 volts, significantly higher. Voltages can go up to maybe 400,000 volts in overhead power lines. Voltmeters measure the voltage difference between 2 points in a circuit. Remember, components use energy, so voltmeters measures how much energy, if you like, has been lost as electrons move through a component. So let's look at how you connect up a voltmeter. The voltmeter is connected in parallel. What that means is you've got one connection before the component and another connection after. So here you can see there's point A and point B, and it's measuring the difference in the energy, if you like, between the 2 points. Now sometimes we refer to it as the voltage across the bulb, sometimes it's the potential difference across the bulb, sometimes it's the voltage dropped across the bulb. It all means the same thing. Now the voltmeter is not truly part of the circuit because ideally no current flows through it. Right, so all of the electrons coming from the supply will simply go around a simple loop here. It's still a series circuit, even though this part is connected in parallel, none of the electrons go this way. Okay, none of them follow the path through the voltmeter. They go through the light bulb instead. So let's talk about resistance. Materials that allow the flow of electrons easily are called conductors. Materials that block the flow of electrons are called insulators. And materials that reduce the flow of electrons are called resistors. Now, resistors convert electrical energy into heat energy. That's why your TV or computer gets warm. And large resistance means a smaller current. Well, this leads us to Ohm's law. Now, there's a mathematical relationship between voltage, current and resistance. We know it's V equals IR, where V is the voltage in volts, I is the current in amperes, R is the resistance measured in ohms, and we use the Greek letter omega as the symbol for the units. There's a very important equation. You have to use this one. You'll be using it in S3, S4, S5, S6, and indeed at university if you go into university. You have to be able to rearrange it for I and for R. We've got the triangle here to help you do that. So if it's I, it'd be V over R. If we're looking at R, it's V over I. And if it's V, of course, it's I times R. Make sure you're comfortable using the triangle method if you need to rearrange. So here's a wee example. Calculate the resistance across the 150 ohm resistor when the current is 40 small m A, so that's milliamps. This is a nice question. So V is what we're being asked to work out the voltage across the resistor. I is the current. The current is 40 milliamps or 0.040 amps. The resistance R is 150 ohms. So all the information's here. Now we can start to solve it. V equals IR. I is the current of 0.04. 0.040 is the same thing. Times 150 gives you 6 volts. Easy? Oh, I think it's easy, but that's fair enough. That's me. I've been doing it for years. The difficulty there, of course, is converting the milliamps into amps. We have to remember what the milli part means. Now, you could have wrote that as 40 times 10 to the negative 3. But that's maybe just going to confuse you there. So more about resistance. It's not only resistors that have resistance. In fact, all components will have some resistance. Even connecting wires have a very little resistance. Now, usually it's okay to ignore the resistance on wires, but it's not in other components. You have to remember, every single component has resistance. So, let's look at series and parallel circuit. When a current has only one path to follow, we say the circuit is connected in series. When the current has more than one path to follow, we say the circuit is connected in parallel. So here you can see there's the negative side. All the electrons must go this way, they must go down here, they must go through all of these, and let's come back here. There's nowhere else for them to go. One single pathway, one loop. Series. But here, the electrons come along here, have to come down here, but here, some of them might go this way, some will continue down. Some will go this way, some will continue down. Now, there's 3 different pathways. Some go that way, some go this way, some go along the bottom way. Either way, they all come back to the power supply. So there is 3 pathways. It is a parallel circuit. But if one of the components breaks in a series circuit, then the whole circuit breaks, because there's no paths for the current. So if you break that circuit right there, none of the electrons can get past it. No electrons can get through any part of the circuit unless you've got a pathway. In this one, however, if you break that component here, the electrons can still continue to go down through the bottom 2 resistors. So these 2 will still work. Even though that one's broken, it will not work, but the other 2 will continue to work. Does that make sense? I hope it does. Now, in your house, your household is wired in parallel. The easy way to figure this one out is to try and switch off one light, and you notice that all the other lights do not go off. which you switch off one light, it's the only light that goes off. That's because everything's in parallel, which means they've all got a different branch, similar to what we had here. So that could be your bedroom light, you switch that off, but your the hallway light and the bathroom light can stay on, for example. So every appliance in your home has a 230 volt supply because it's connected in parallel. So going back to this component here is connected directly to the power supply. So if this was a 230 volt supply, that would be connected directly to it. So it would have a 230 volt across that. Similar, so with that's also wired directly to the power supply. So it would be 230 volts across that. And that would be the same in all household components. In your house, everywhere, it's parallel. It all gets 230 volts. And we know it's parallel because we can independently switch things on or off to suit us. Hope that helps.